Ever rubbed a balloon on your hair and watched it stick to a wall? It's a classic science trick, but there's real magic happening behind the scenes. That simple act is a fun introduction to the invisible forces all around us. Or noticed a comb picking up bits of paper after you've run it through your hair? That's static electricity in action, showing how everyday objects can interact in surprising ways. When you rub two objects together, you're actually transferring an invisible property, electric charge, between them. This happens because electrons, tiny particles in atoms, can move from one surface to another. This charge lets objects attract or repel others, even if they seem neutral at first. It's why a charged balloon can pull tiny scraps of paper or make your hair stand on end. Static electricity is simply the build-up of this charge on an object's surface. The more you rub, the more charge can accumulate, waiting for a chance to move. The shock you feel after walking on a carpet and touching a doorknob, that's a sudden movement of built-up charge, called discharge. It's a tiny spark, but it's the same principle behind lightning in a thunderstorm. These everyday effects show that matter can gain or lose charge through simple actions like rubbing, walking, or even just moving objects around. The study of these charges at rest is called electrostatics. Scientists use special tools and experiments to explore how static electricity works and how it can be controlled. By observing these simple phenomena, we begin to understand electric charge, a concept at the heart of modern technology, from photocopiers to touchscreens. Static electricity is our first glimpse into the powerful world of electricity and magnetism, opening the door to discoveries that shape our everyday lives. Electric charge is a basic property of matter, just like mass. Atoms are made of protons, positive, electrons, negative, and neutrons, neutral. In a neutral atom, the number of protons equals the number of electrons, so their charges cancel out. When this balance is disturbed, by rubbing or contact, electrons move, and the object becomes charged. Gaining electrons gives an object a negative charge. Losing them leaves it positive. It's almost always electrons that move, since they're on the atom's outer edge, and can break free. All matter is packed with positive and negative charges, but we only notice them when they're out of balance. This simple atomic model explains all electrical phenomena. Electric charge leads to a simple rule, like charges repel, opposite charges attract. Two positive or two negative objects push each other apart. A positive and a negative pull together. Suspend two pith balls and charge them the same way. They repel. Charge one positive and one negative. They attract. This force is what holds atoms together. Electrons are drawn to the positive nucleus. Without this attraction, matter wouldn't exist. Even when a charged comb attracts neutral paper, it's because the comb induces a separation of charges in the paper, leading to attraction. This law of attraction and repulsion drives all electrostatic phenomena. Understanding it is key to predicting how charges behave. Electric charge has four key properties: additivity, conservation, quantization, and its scalar nature. These fundamental characteristics help us understand how electric charge behaves in different situations, from simple experiments to complex electrical systems. Additivity means the total charge in a system is simply the sum of all individual charges, taking their positive or negative signs into account. This property allows us to calculate the net charge in any group of objects or particles. Conservation states that electric charge can't be created or destroyed. It can only be transferred from one object to another. This is a universal law holding true in all physical and chemical processes. For example, when you rub a glass rod with silk, electrons move from one material to the other, but the total amount of charge in the system remains unchanged, just redistributed. Quantization means that charge exists in discrete packets. The smallest possible unit is the charge of a single electron or proton, known as E. You can't have a charge smaller than this basic unit. Any object's charge is always a whole number multiple of E, never a fraction. This is why we say charge is quantized, not continuous. You can't have a fraction of this basic charge, making it indivisible at the most fundamental level. Charge is a scalar quantity. It has only magnitude and sign, but no direction in space. This makes it different from vector quantities like force or velocity. This property makes calculations straightforward. Just add or subtract the values, without worrying about direction. These four properties form the essential foundation for understanding, measuring, and working with electric charge in science and technology. Materials are either conductors or insulators based on how easily electrons move through them. Metals like copper and gold are conductors. Their electrons move freely, allowing electric current. Insulators like rubber and glass hold electrons tightly, blocking current. That's why wires are coated in plastic to keep electricity where it belongs. Semiconductors like silicon can act as either, making them vital for electronics. The Earth acts as a giant reservoir for charge. This is the idea behind grounding. Grounding lets excess charge flow safely into the Earth, neutralizing objects. If a charged object is grounded, electrons flow to or from the Earth until neutrality is restored. Grounding is a key safety feature in electrical systems. Understanding these material types is crucial for controlling electricity. Objects can be charged by friction, conduction, or induction. Friction. Rubbing two materials transfers electrons. One becomes negative, the other positive. Conduction. Touching a charged object to a neutral one lets electrons flow, sharing the charge. After contact, both objects have the same type of charge. Induction. Bring a charged object near a neutral conductor. Charges inside rearrange without touching. If you ground the conductor, some electrons leave or enter, leaving it charged after you remove the ground and the original object. Induction charges objects without direct contact. This method is useful because the original charged object doesn't lose its charge. These three methods explain how everyday objects become charged. Mastering them is essential for understanding static electricity. To measure electric charge, we use the Coulomb C. 1 Coulomb is the charge moved by a current of 1 ampere in 1 second. Q half-rayos I xt. At the atomic level, a Coulomb is huge, about 6.24 x 10^18 electrons. Lightning can transfer several coulombs in a flash, showing the scale of natural electric events. Electric current is the flow of charge, measured in amperes. In wires, this flow is moving electrons. The ampere tells us how many coulombs pass a point each second. This flow powers everything from light bulbs to computers. Knowing Q, or IXT connects static charge to moving current. The Coulomb is a practical unit for quantifying electricity in real-world systems. How strong is the force between two charges? This is a fundamental question in physics, and the answer helps us understand the invisible interactions that shape the world around us. Coulomb's law gives the answer, providing a mathematical way to describe the electric force between two charged objects. The force is proportional to the product of the charges and inversely proportional to the square of the distance between them. This means that both the amount of charge and the distance separating them play crucial roles. Double the charge, double the force. The relationship is direct and easy to visualize. More charge means a stronger force. Double the distance, the force drops to a quarter. The force weakens rapidly as charges move apart, showing how distance dramatically affects interactions. The formula, F KQ1Q2, summarizes this relationship in a single equation, das R2, where K is about 8.99109 N and G2C2. This constant makes the units work and sets the scale for electric forces. The force acts along the line joining the charges, repulsive for like charges, attractive for opposites. This explains why similar charges push away and opposites pull together. This law lets us calculate the exact force between any two-point charges, no matter how small or large. It's the foundation of electrostatics, just like Newton's law is for gravity. Both laws reveal the deep connections between objects in our universe. Coulomb's law explains why charges attract or repel so strongly at close range, making it essential for understanding electric fields and forces. It's the starting point for analyzing any system involving electric charges, from simple atoms to complex molecules, and even large-scale electrical systems. Electric charge shapes our world, from dramatic lightning to everyday tech. In storms, friction separates charges in clouds. When the difference is big enough, lightning discharges it in a flash. Photocopiers use static electricity. A charged drum attracts toner only where needed, transferring the image to paper. Even a shock from a doorknob is a mini lightning bolt. Charge built up on your body jumps to the grounded metal. Dry air makes these shocks more common, as charge can't leak away easily. Electrostatics powers paint sprayers, air purifiers, and touchscreens. Capacitors, found in all electronics, rely on storing and releasing charge. Understanding electric charge isn't just academic, it's key to modern life and technology. From nature to gadgets, electric charge is everywhere.